Hello, welcome to the third part of the IPC section discussion. Here we are going to get into the details of what are semaphores, what are the two important functions which are nothing but system calls, and then this is how is this used in a typical scenario. Okay, so before I start with the discussion on semaphore, first thing we need to understand that we need to create a semaphore before using these functions. As I told you, semaphores are the resources, like when you create a file, it's a resource in the hard disk where you need to take the help of OS to create a file for you, and you will give the name, you will put it in a particular directory, and then it is your choice to use that file for whatever purpose you are interested in. That OS is not bothered about, but based on what you want to use it for, you may create a PPT file or a text file or a Word file. So similarly, a semaphore is created first of all, and then it gives you a handle, like file is given a handle in your program if you are using a file, or you may be having a name which you are using it for editing purpose or saving it or sending it to some across some particular on a mail or something. So similarly, semaphore is a resource which is maintained by the OS, created by you and supported by the OS. Then it gives you a handle, then it provides you some interfaces, which is a system call again. What are the operations that you can perform on a semaphore? Similar to file, where you can copy a file or rename a file or delete a file or append the file. So these are the operations that you do on a file. Now, what you do on semaphore, you need to first, maybe I will call it as a sem init, which later on I will show you a code which uses this function to create a semaphore and initialize a semaphore with some value. So when you are creating a file, you might create it with empty content, or you may even feed in whatever is fed into the keyboard will be given to the file and stored in the file. Okay, that also you can do. So sem init is a semaphore which is created, and then you are initializing with some value. Then we are going to have sem wait, which is a function to wait on a semaphore. Okay, and then when you want to release it, maybe some signal, we'll call it a sem signal, which is to say that I am freeing up a semaphore. So these are the functions which we are assuming that we will be operating it on. So these are the functions provided, and you need to say which semaphore you are operating on, whether you are maybe I have created S1 and S2, then S1 is a semaphore which you are going to be waiting on, or you are going to release a semaphore, then you are to say S1 is being released. So the processes first creates a semaphore, and then that handle is made available if it is supposed to be used across the processes. Then you can operate on that semaphore. Basic functions are these two only we are going to talk about in this discussion today. Now, what are we, why are we using it? As I told you, semaphore is something like a lock which makes sure that only one process acquires it. When I say acquire the lock, means you own the lock. That means nobody else. Now it is like you getting into the house by locking the front of the door of the house. You are inside the house. Now assume that nobody else has a key to that room, and you are inside the room. You make sure that when you enter the room, you lock it and go inside. That means you are going to, you have taken up the role of owning the room or owning the lock, okay, access to that particular room. Then you spend some time, then you, what do you say, if you are done with the job inside, then you unlock it and come out. Now anybody else who is waiting outside the room will get a chance to enter into the room. So the semaphore here, there can be two varieties of semaphore, binary semaphore and counting semaphore, which we will cover as we go to the later part of this discussion. So binary semaphore means only one process can be allowed to enter the critical section. When I say the room, means it is a critical section. That piece of the code which is going to be accessing a common database, or common data where you want only one process to modify it. And then if it is a counting semaphore, then we are saying that n number of people can be allowed to acquire the semaphore. So now there should be a state, correct? The semaphore, I said nothing but is a software implementation, okay? And it can be initialized like a variable. When you create, you initialize it with some value. Semaphore also can be created and initialized with some value. Now what is the value that you want to keep it, based on whether you are creating a binary semaphore or a counting semaphore. Now if it is a binary semaphore, that means there is a count of 1. That means semaphore is available. If it is free, I say that the value of that semaphore is 1. So when you lock it, what do? You decrement it by 1. That means you make it 0. That indicates that that particular semaphore is owned by some process. It's not free, so it is busy. That means any process comes and looks at the lock or the semaphore, and if its value happens to be 0, that means it is already owned by someone. The process who is coming to look for the lock will always be interested in that only because it wants to enter the critical section protected by that particular lock. So, but the semaphore, when I say semaphore and lock, please understand that I am referring to the same context. So, the system developer has mapped it for protecting this critical section. I am going to use this particular semaphore. It's like one lock for a particular room. And then any process, if it wants to use that, enter the critical section or modify a particular common database, it is supposed to acquire the lock. Then what it will do, it will come ask for some wait. I am going to, it is coming in to say that I am waiting, assuming that it is already busy. But if it is free, what happens is it is not going to wait. That process, if it is the first process to ask for the semaphore, then it enters by making it 0, making it busy. Then any other process after this calling for some wait on that semaphore is going to be blocked. Please remember, it's not going to be busy wait, because if you are doing a busy wait, that means it is continuously looping, looking for that variable. Now what is the problem with the busy wait? The process will be running. That means you are wasting the CPU time. You are not allowing any other process to run in that on the CPU, and no progress is made, right? It's continuously running. And maybe if you have a multi-core, some other process which is owning that semaphore runs and releases it, then you may get a chance to acquire the semaphore. So the busy wait is not a solution here. You don't want the process to run continuously in a running state, waiting for the semaphore. Then the purpose of having a semaphore itself is lost. So what we are going to do is, busy wait is a pseudonym or a pseudo code to say that it is waiting for the semaphore. The process cannot go further, but that doesn't mean that it is running on the CPU. It is going to be in a blocked state. When the process is waiting for some other process to release the semaphore, this any number of processes, it need not be only one, it can be any number of processes waiting. It's like a queue of people waiting outside the room. Because the room is locked, somebody is inside the room. Then you have to wait for that process which is inside the room to release it, come out. Then whoever is in the waiting queue, based on either priority or based on who came first, the queue will be maintained by the OS and one process will be allowed to enter. So that is what is happening in the system. And the process being in a block state means it is not going to occupy the CPU. It is going to be moved out from the ready queue and it is going to be in the blocked state. And if it is a counting semaphore, what happens? That means you can allow n number of processes. So when you are initializing it with some unit, and if you know that you are creating a counting semaphore, you may be initializing it with some value, maybe n, which is 6. Suppose 6 number of processes can be continue to acquire. That means there can be 6 processes who can own the semaphore, continuous owners. Okay. So it is not meant for critical section protection, because you cannot allow 6 processes to run and then they change the database, but it could be for n number of resources you have. Maximum you can allow n processes to be allocated or allowed to use the resource, and then more number of processes come asking for the resource which is not available, then they will be blocked. So that is for counting semaphore. We'll come to that when we have discussion on counting semaphore. I think this sets the stage for understanding the rest of the discussion. Okay. So let me go quickly. Each process observes the following protocol. They need to follow this rule that if you are going to access the critical section which is protected by a semaphore, it is the responsibility of the developer who is writing the code to make sure that semaphore is acquired first before you access the database. Now, what if I do without that? No issues. OS is not going to come and tell you, hey, you are supposed to own this particular semaphore before you access this database. No, it's not going to say. If you don't follow the rule and you come in and then change the critical section or run the code which changes the common data, you are taking a risk of corrupting it. You are not following the system design constraints, right? So this is done by the system developer or system designer who says that okay, these are the protected data which needs to be protected with this semaphore. Then you are to take care of, as a developer, you need to take care of acquiring the semaphore before entering the critical section. So what is the negotiation? Somebody, it can be based on priority or based on the who comes first, FIFO order or LIFO order, whatever you call it as. Then only one process, if it is a binary semaphore, will be allowed, and then it owns the semaphore and then it gets into a critical section. Then, and again, it's a responsibility of the developer to make sure that what you acquire, you release it. Suppose I come inside acquiring the semaphore, okay, wait I executed, and then some wait I executed, I acquired the semaphore, I entered the critical section, I executed it, but I forgot to release the semaphore. Some signal I did not do. Then what happens? You are owning the semaphore and you have forgotten that you have somebody is waiting. Now what happened? This is the door. You entered the room, but there is a back door. Without opening this, you went out, or maybe through a window you jumped out. These people who are waiting here is properly wanting to enter into the room by having the key, or they are asking, they are waiting for you to come out. Whereas OS does not know that whether you inadvertently no release the thing, whether you forgot to release the semaphore or not, it doesn't know. It may be thinking that OS is not keeping track of how long you are going to be there. If it is required, it may be done. Then what happens is that all the processes which are waiting for this semaphore will be blocked forever, because this is never going to be released, but you forgot to release the semaphore, and then you continue to do a job which is outside of the critical section where you don't need to own the semaphore. So these are the discipline that needs to be taken care of by the software developer who is using the semaphores. Okay, I hope you understand what I mean by a semaphore and what are the operations that you can perform and what are the precautions you need to take while using the semaphore. Okay, basically binary semaphore is meant for mutual exclusion. Okay, and then there is one more usage which will come to that. Now mapping of semaphore with the shared data is application's responsibility. Application processes need to take care of acquiring relevant semaphore before accessing the shared variables protected by the semaphore. Okay, you cannot acquire some other semaphore and which is not meant to be designed for protecting a particular database. You acquire it something else, but you change something else, some other data which is protected by some other semaphore, which is also not correct. Okay, you need to have that idea and properly write the code. So application processes need to map a particular semaphore with a resource that they want to access simultaneously. Now, where do you need this semaphore at all? Suppose if you have a data which is going to be accessed by only one single process, and you don't expect that data to be accessed by multiple processes, and they are not running concurrently, and it's not going to be used forever, for sure, then there is no need for you to protect it, because you know that only one process is going to be using it. But once you know that it is going to be accessed by multiple processes, you cannot even imagine or think that whether will it run at the same time or not, or no, it's not going to happen. If they are not going to run simultaneously, they are not going to concurrently use it. You cannot have that assumption at all, because once you create a multitasking application, you are giving the freedom for the users who is using your application to run it on either single core or multi-core or any kind of processor. And once that freedom is given and you don't know what is the speed at which these processes are running, what stages they are in, and what is the probability that these processes can be at the same time when they are accessing these critical data, you cannot have a control on it unless you are designing your system such a way that they don't simultaneously access the particular common data at the same time. So you need to assume the worst case scenario of multiple processes running on multi-cores, and there is a possibility that both of them may be accessing this common database simultaneously. Though it may not happen, it is a possibility that even if there is a probability of a smallest probability that they could come together at the same time when they are running on multiple cores and then access the database, and that could corrupt the system, then you are not designing the system which is reliable and consistent. So that needs to be taken care of. So semaphore is essentially a variable maintained by the OS in software and implemented with the help of hardware. Access and operations on semaphore is permitted only when it is free. When I say it is free means access means you are free to come out of that some wait only if it is free. Otherwise you are blocked. The process, if a process locks a semaphore, that means it acquires it, others cannot enter, get access to it. Okay, and simple methods are signal and wait. Wait is for acquiring the semaphore. Signal is to release the semaphore. Maybe the order is different. I am showing this from a book. And now semaphore is the unit, and there are processes which are in the waiting list. Okay. Now there are two functions. Once you enter it, you use the critical section and exit it. Now, which function will you use for entering? Of course, you know that you need to wait. Now, you are calling a semaphore wait, assuming that there is somebody using it. If there is no one using that or acquired the semaphore, then you are not going to be blocked. It will be immediately you will come out of the wait function acquiring the semaphore. Okay, so wait on semaphore. Sem is some variable on some particular semaphore, and signal semaphore. That means you are saying that I am going to release this semaphore now. Why are you releasing it? You are informing the OS. Please remember these wait and signal function calls are system calls because you are using a system created resource semaphore. Similarly, when you are using a file, it is a system created resource. You cannot access the file on your own. You need the help of OS. You want to write it or read from a file or write into a file or delete a file or rename a file. So all these function calls which are system calls, and you are giving a control to the OS, it goes into the kernel mode and the function is executed. Now, if some other process has already executed the semaphore, then anybody else coming and asking for a semaphore will be blocked. It will be in a blocked state. Okay. So identify the method which are going to be used, and I think it is shown there. When a process wants to enter a critical section, it waits for the associated semaphore to be free. Then once a process locks the semaphore, it owns the critical section and enters the critical section. It owns the lock also, it owns the semaphore also. When a process is in CS, here it's not computer science, it is a critical section. Or when it holds a semaphore, both are same, then other processes are prevented from entering the CS critical section. Now, what are the different usages? We'll see. A process frees the semaphore on exiting the CS. This is expected of the proper behavior, right? You are supposed to exit the CS. One of the other processes, only remember, one of the other processes, I am assuming here a binary semaphore. So, one of the other processes waiting on the semaphore then can block it and can enter the critical section. This ensures that a notion of atomicity or indivisibility is achieved. See, what I mean by indivisibility, atomicity, when I enter the semaphore, want to enter a critical section, I acquire the semaphore. To when I want to acquire the semaphore, that waiting is done. Now, remember, somebody is waiting and someone is releasing. So, okay, maybe I assume that P2 is the process which is waiting on the semaphore. Already P1 is acquired it and it is in the critical section. Okay, it is already in the critical section. Now, it is going to say signal. Okay, let me say S1 is the semaphore. I am signaling semaphore S1. This is done by the process P1. It is going to be indirectly impacting the other process P2, which is on waiting on S1. Okay, let me say waiting on S1. So, some job, something happening on one process is impacting another process. When I say impacting, it was in a blocked state, okay, waiting on the semaphore. Now, when this guy says signal S1, you are calling the system call, which is you are giving a control to the OS. Now OS knows which are the processes waiting on that particular semaphore, because if there's a list of processes, list of processes there in that. So now what does the OS do? When you get into this signal, you come out of the signal as a P1 and you can continue with your job. But you are indirectly made some changes to some other process because of this action. How? Because P2 was waiting on the semaphore, OS not only assumes, or not only assumes, it comes to know that okay, you are interested in releasing the semaphore. You are no longer going to be using this data, or you are not going to be in the critical section. You are guaranteeing it. It doesn't care about it, but you are as an application developer should guarantee that you don't do anything with the critical section here. So you will go carry on with your job. I have done my job. I am getting out of the room. Where you go doesn't matter. Now there is somebody waiting. Then it is the responsibility of the OS to make sure that I wake up the process which is waiting on the semaphore. So releasing the semaphore and waking up this process, they happen inside the OS kernel code, and it happens atomically. Okay, so no other in between something can happen. That error, no problem of somebody coming in and screwing up some things or not is not going to happen. So P2 is going to be woken up. Now when I say woken up, it was not sleeping on sleep for 1 second or something, but it was blocked for a reason that S1 is not free. So it should be now moved to block to ready state. Okay, it should move to ready state, and then whether that process will be scheduled immediately or not is not in your control. It depends on the priority of the process which is getting woken up, or it depends on the scheduling algorithm running. It doesn't matter, as long as the process has come into ready state. It is now still in the wait function call, okay, inside the wait function call from the P2 perspective, but it has not come into the critical section area of the code to execute whatever it wants to do after the wait. So it is in the ready state, still it is not running. When it gets a chance to run, it will wake up from wait. Similarly here, it was in a running state and it continues to be in a running state because it is only just releasing the semaphore and continues to go further. So because of this particular process doing something, it might, suppose imagine that P1 was a low priority, okay, for argument's sake, and this guy was a high priority process. What would happen is the process which is P1 getting this function call, system call signal, may not come out of the signal because of the reason that it has made another higher priority process to become ready. So what happens is while releasing it, it has made some other process, high priority process to become ready, and it may get a chance to run on the CPU if it happens to be a single core CPU. So this process may continue to run or not continue to run. It may wake up from wait call and enter into critical section. And this guy, because it made another higher priority process to become ready, it may get blocked. It may get in a ready state, it may not get a chance to run on the CPU, but it will not get blocked. Please remember, blocking state it will not go into, but it will continue to be it will come back to ready state and wait there. Okay, so I need you to think a little bit about it. Okay, I'm sure you have understood about the different state transitions, and you should be now in a position to relate these two. Okay, so now processes need to follow the discipline of acquiring the semaphore before critical section and releasing it after doing the job with the critical section, after completing the job with the system. Okay, so the system architect is the responsible person to make sure that these rules are followed and documented across the team, because different team may be working on different processes, developing code for different processes. They need to take care of it. So critical sections need to be short as possible, preferably, because we don't want some process to hold the lock and take longer time. So you are not supposed to sleep inside the critical section because that's not allowed. Okay, which I mentioned in the previous lecture also. So need to take care of potential deadlocks. Suppose if you are using multiple semaphores, what would happen? Suppose I have a semaphore S1 and semaphore S2. Okay, so suppose if I have a critical section which is so where it's like a double protection in a when you're accessing a bank account, right? What does the bank do? You give up username, password, then you come into the system, but still it doesn't allow you to access the account. It's a one more level of security. It will send a OTP to your mobile number. Even if your password is compromised, someone asks your password, they cannot enter the your account and do some transaction and transfer your money to some their own account. Why? Because there is a OTP, second level of protection. OTP is sent to the mobile of registered mobile of your account, which will come to you, not to the person who is trying to hack the bank account. So even if your password is protected, this OTP protects you from illegal access of your bank account. Similar to that, you may have some occasion wherein you need to have two semaphores to be acquired before I get to the critical section. If that is the case, what will happen is you need to have a discipline in calling that wait semaphore in some particular order. Wait S1, then wait S2, okay, then enter the critical section. So if suppose process P1 wants to acquire the semaphores S1 and S2, they should call it in this sequence. Similarly, some other process P2 wants to enter the critical section, it should also call S1 wait and S2 wait, then come into the critical section. Now, why should I make sure that or guarantee that these semaphores need to be called in that particular sequence? There is a reason behind it, because if I do it wrongly, suppose P1 is doing it, wait S1 I do, okay, whereas in P2 I know that I am supposed to get two semaphores, acquire both the semaphores before entering the critical stage. That much I know, but I don't care about what order I do wait S2 here. Now both the processes know that both S1 and S2 should be acquired before entering the critical section. That is the rule given to the developer, but they, by mistake they interchange the order. Now what happens, this process will say that okay, now I have acquired S1, I need to now wait for S2. This process will say okay, I acquired S2, let me S1 also let me get it, then I enter the critical section. Now there is a problem. What is the problem? I always want you to think that anything executing as two different processes, they can execute in any core, and the sequence of execution can be interleaved. Okay, the time wise, I'm not saying that if you draw the actions on S1, if I S1 and S2, both P1 and P2 are running, maybe they are running on two different cores. If I say that this I call it as activity 1 A1, this is the activity A2, then I call this activity 3 happened and this is the activity 4 is happening in sequence of time. Now what will happen is A1 is happening, A2, A3, A4. Okay, let me write it as A1, A2, A3, A4. In this sequence, if it happens, what will happen? What would happen? Now at A1, this P1 has acquired the semaphore S1, because I assume that it is not owned by anybody. And then at A2, this executes and it acquires the S2. Now at A3, what will happen? It is waiting for S2 to be available, which is owned by P2. Remember, already it has acquired in time wise. Now what happens? This guy says, okay, I remember that I need to acquire both the semaphores. Let me do it in this order. So it has, you are written the code like this. Now you are asking for S1. What will happen in this situation? This is P1 is waiting for S2 to be released by P2, because which is owning it now. Whereas P2 is waiting for S1 to be released by P1, which is owning it. What is happening here? It's a deadlock. So when you have multiple semaphores, And if you are trying to acquire them or release them, there is a discipline required that they are to be done in the proper sequence, and the sequence should be, it need not be, I'm not saying that you need to do, always do s1 after s2. You can do it s2 after s1, but the sequence should be decided and followed by all the processes which wants to acquire those semaphores, one after the other. Remember, it is not, this sequence is not compulsory. If they are not for a, they both are need to be acquired, and then you enter the critical section. If you are acquiring one and then releasing it immediately, there is no problem. But if you are owning a semaphore and then trying to get another semaphore, then only this rule has to be followed. I'm not saying that no, the semaphores which are not related and no, they are not expected to be owned together, you don't need to bother about it. But if they are need to be owned simultaneously, you need to follow a sequence, and that sequence should be followed by all the processes when they are acquiring those semaphore. Okay, this is will lead to a deadlock, which is going to be a no discussion in the future in some discussion. So I thought I will preempt it and bring it here so that that part of the discussion will be easier to complete. Okay, so now critical section need to be as short as possible, and if you are using multiple semaphores, this is a, scenario that I have explained it just now. I hope you understood it. Now, basic functions of semaphore, let us go fast. Is basically an integer value. The semaphore variable is, because why am I keeping it as an integer? Maybe I may have it as a binary semaphore or a counting semaphore. Remember that it's decided based on the init value. So I cannot have a boolean function, variable as a semaphore. Then it is chosen as a binary semaphore. I can't use it as a counting semaphore. But if I want that semaphore to be used either as a binary semaphore or a binary counting semaphore, then I need to have an integer as a value, right? So wait on a semaphore. Then what you do? You are decrementing the value. Okay. So let me come to that later on. Now I am bringing out one more symbol. Okay, it's called Dexter's convention of p and v for weight and signal. Okay, this is just I'm introducing this on more usage of semaphore, because it may be you may come across in any of the OS literature or any paper that you read about operating system or a semaphore, or you happen to read a book on operating system, which likely to be very rare nowadays. But I urge you to read at least one book or the other on any topic which will make you stronger in that particular topic. Okay. So semaphore functions, semaphore variable s is initialized with a value of 1 if it happens to be a binary semaphore, or a non-zero value. Okay. If it is a counting semaphore, which can be a, of course, when they say non-zero, it also implies that it's a positive value. Okay. So weight operation on a semaphore decreases its value. So when you come on waiting, you decrement it. When you go out after using the critical section, you increment it, because to indicate that okay, now the semaphore is free, it's not busy. Okay, I remember that particular sequence. And here one thing which I want to bring it your notice, that what is shown here is actually a pseudo code. Please don't think that this is the code inside the wait function. If this is the code inside a wait function of a implementation of a system call, then it is not helping you at all, because it's going to be a busy wait and the process is going to be continuously running. This is a pseudo code to indicate what is actually what I mean by wait. When I come inside a wait, the process is not going to execute this instruction. If it is already busy, it's going to be in a blocked state. It's not going to be running state. I hope I don't need to restate it again. This is implicit, and I hope you understand it. So when you come in, it is going to be decremented by 1 and then enters the critical section. When you release it, you increment it and go out. Okay. So this is then the block process. Anybody is there will be woken up, as I explained you in the earlier discussion. So their operations are atomic, and it can be evaluates a negative or zero semaphore value. Okay, negative is given as a error condition kind of a thing, which is not likely to be getting into. Okay, the value becoming negative is not possible, but still it is shown as a generic rule. So a blocked process can be unblocked when some other process executes a signal operation. Okay. I already explained it. Now what are the different usages? I just gave an example. I thought I will give you P1 and P2 you want to use, which I already explained, but I am showing you a code which I am sure is self-explanatory, which you can understand it. And so, what should the initial value be? It should be one, because you when you are creating a lock, if the Godrej company is giving you a lock, it should give you a key also and keep it in an open condition and give you, so that you lock it and unlock it multiple times to make sure that what you have, the key and the lock are matching. But they cannot give you a locked one and then don't give you a key. Then what is the use of the lock? So when you are creating it, maybe some occasion you may create it with locked state, but I am saying that if you are using it for critical section, you should be in a free state to start with, and then somebody entering the critical section will lock it and use it. So to start with, there can be no process inside, so it should be anybody entering the wait first time, they will get the lock and get into the critical section. And I'm creating a semaphore kind of use, then both processes wants to enter a critical section, they should use um, the same semaphore use. So the general structure of a process should be like this. You execute a wait, enter the critical section, and release the use, and then you go back and do your job. Okay. Imagine that it is happening continuously. That one process is executing a code, and then whenever they want a critical section, they wait on the semaphore and then they release a semaphore. That's all. So this is actually being explained. This infinite loop is I am talking about this infinite loop, either process P1 or P2. Imagine that the same code is being executed. It's a re-entrant code and same process, and different processes with the different data. Maybe they are executing the same piece of code. Then also it should work. Okay, it doesn't matter whether same piece of code is being used as a re-entering entrant code, or two different functions, and you are using this function call like this. Okay. So whenever one process enters, I'm just giving you a sequence of operation happens. Initially, neither process is in the critical section, so use will be valued 1. Assume P1 tries to enter the critical section first, then wait will be called by the process P1. Will it come out or will it get blocked? Because nobody is there in the critical section and P1 is executing the wait function call for the first time. It will be acquiring the semaphore. It will also make the use variable inside the user. It's not visible to you inside the kernel. So use will be made 0 because decrementing it while coming in. And P1 succeeds. When I say succeeds, means it wakes up, it comes out of the wait function call without getting blocked inside. Okay. It was in running state. It continues to be running state and comes down after the wait. Then they enter the P1 enter the critical section. Imagine later P2 wants to enter the critical section while the P1 is using it. Then what will happen? CS is also P2 is also expected to call the wait function call. It calls it, but it will get blocked because use is 0 now and P1 is still owning the semaphore. So it is in the critical section. Indirectly it means that. So P2 gets blocked and P1 executes signal. Now P1 is done a job within the critical section and it executes a signal function call. Then use will be made as 1. Then it indirectly impacts the P2, which was in the block state, will be made as a ready state, and then I made it as a blue because some changes are there with the previous content. So I made it as a blue to indicate that these are the changes done in now this piece of presentation to make sure that you understand by block state or ready state are not the busy wait. Okay, the processes are in the block state whenever they are waiting on a semaphore which is already acquired by someone else. So this sequence continues. Okay. Now another scenario I want to show you, that if suppose I want to use the semaphore for synchronizing event. That means let me give an example. Now suppose a piece of code is there, statements of some statements which is called S1. I want all the statements of S1 to be executed by P1 first before P2 starts executing the instructions which are in S2. Now I want to use the semaphore here. Now what are the conditions? Now suppose if I have a semaphore which I created as the sync, what are these? What is that function call I should do before I make sure that S1 completes S1 and then this P1 completes the instructions in S1 before P2 starts with this. That means what? I want the P2, if it comes first, to get blocked here. Okay. And then P1, if it is coming first here, it should signal here and continues further. Okay, if that I want this, who should have been the owner of this semaphore that I am trying to use in this place? A sync semaphore. Then what should be the function call? No, I think if you remember, there are two function call, either some wait or some signal. Which one should be done there? Okay, I think you can easily predict it. Okay, let me show you. And initially what I should do is I should make it as a zero on creation. That means the semaphore is already acquired. Okay, imagine it is initialized with the value acquired. That means the p1 would have used it, is not, p1 is not using any semaphore related function call before it comes here. Okay, so it should have been, in a acquired state. That means it's zero. That means it's busy to start with. Okay, then, and one more reason, one more thing you should remember, that the semaphore that I have, the handle, should be accessible to both the processes. Okay, imagine if these processes are two different processes, then they don't have access to that common data or something, right? Unless there is a, this process happens to be a thread within that process. Okay, another process. So if they are two different processes, they don't have a access to the common area. So what you should do is this sync semaphore handle should have been in a some shared memory. Okay, that when I explain the code, maybe it will be clear. Imagine somehow you make sure that sync is known to both the processes. Okay, otherwise you can't access that sync semaphore itself, because somebody is creating a semaphore. Maybe p1 will be creating it, but it will create it in a busy state. Okay, and then that semaphore should be available to this p2 also, so that it can wait on the semaphore. So it creates it in a busy state, and this handle, whatever is created semaphore, is available to this process, and it can call a wait function call. Why am I saying this? You do not have any preconceived notion that P1 will come first here and then only P2 will come. You cannot have that assumption. P2 can come here and then can get blocked, or it may not be even running, or it may not have come here at all. But P1 would have already released it. There is no problem if it is released before. But by mistake, P2 should not come here and do this S2 before S1 completes it. So that's why we are using a semaphore to synchronization purpose. So what will you do? You do a signal function call on the P1 side, you say wait on the P2 side. So what is the difference between a semaphore being used for a critical section, okay, and for signaling purpose? Okay, synchronization purpose, or I can call it a signal synchronization purpose. I want to synchronize that S1 is done first before S2 starts. Okay, if you are using a semaphore for synchronization purpose, remember it is being called by two different processes. Whereas if you are which is called the signal call and the wait call are called by two different processes. Whereas if you are using this particular semaphore, maybe use semaphore, please remember both the use and sync semaphores are, in this case, is they are binary semaphores. Okay, use is one semaphore and sync is another semaphore. As I told you, it can be with many resources, many semaphores can be created. Now, when you are using the semaphore use, it is used by wait is also called by the same function, and signal is also called by the same process. Okay, same process in the pair in as a pair. Whereas there is no pairing here. One is calling the signal one process, and there is no matching wait here, right? Here also wait is there. There is no matching signal here, because they are two different processes. They need not to have a matching wait and signal. Whereas if you are using it for a signal critical section, there should be a matching function call, and you cannot afford to forget one of them. Or a comment of this, and then I by mistake I commented off, and then I entered the critical section, which is not a valid reason. Okay, I hope this is clear. Now, in a synchronization purpose, the various signal semaphores are being called by two different processes, and the sequence is like this. Okay, so now why you need a queue based semaphore? Because there may be many processes waiting on a semaphore, so you need to have a queue internally that is done by the OS, not we do it. So, and wait and signal are function calls which are implemented on the semaphore. Okay, so again remember this, whatever I'm showing, if no this if condition, I'm avoiding that while loop with a block state. Okay, here properly written as it is blocked. Okay, and now executed by the process, which is exiting the semaphore. Now binary semaphore, I told you that it can be free or busy, and the values are 0 and 1, and it is used for critical section. And counting semaphores are n number of values can be there, and it can be for maybe using n number of resources. You can allow n number of processes to use them. After that, you will allow any more processes to enter the semaphore. That means acquire the semaphore. So you keep decrementing it as you give semaphore access to the processes, and then when it reaches 0, you stop anybody acquiring the semaphore. They will be blocked. Okay, so n number of printers can be used by n number of different processes, and then once all the printers are busy, you make other processes to wait. So that's the purpose of counting semaphore. I hope this lecture was useful, and you can understand the difference between binary semaphore, counting semaphore, and what is the purpose of wait and signal. And the binary semaphore itself can be used for two purposes, either for signaling purpose or for protecting a critical section. Now, when you are using it for a critical section, the wait function call and matching signal function call system calls should be on the same semaphore and should be paired together. Whereas when you are using it for a signaling purpose, they are called by two different processes, and the handle of that particular semaphore should be accessible to both. How do you achieve it? You can keep it in a shared memory which is accessible to both the processes, which will be explained in the code aspect of it. But this is only to make you aware processes do not have free access of memory areas, and one process creates a semaphore and both the processes use them. So unless other process has a handle, you cannot make this process to wait on the semaphore. So you need to have somehow provide the access of that particular handle of the semaphore created by some other process, used by someone other processes. Okay, so that's it. We come to the end of this discussion. Bye bye.